All right, guys. Well, it is 1 o'clock. I think I'm going to go ahead and get started. I hope that you guys are all doing well and had a nice weekend. I had some time to rest a little bit. I'm still not totally feeling 100%, but I'm doing a lot better than I was. So that's a good thing. Let me start this new week with a quick overview of where we're at and what's coming down the line here. There is a homework assignment due tonight. It has 5 problems on it, plus a little video about Taylor's theorem proof for you to watch. All you have to do for that is just take the notes on it. I think it's 15 minutes long. As far as the 5 problems go, I'm going to do at least the last 2 of them in class for you today. So you don't have to worry about that at all. You're just going to be able to write them down. The first 3 of those 5 problems, if there's questions about those, maybe there'll even be time to look at those as well today. If not, I do have office hours, as you know, later on today, several hours worth of times for you to stop by, either in person or in Zoom. So I don't think this should be too bad. I'm hoping everybody's going to totally nail this this particular homework and hopefully make good sense of it. But you definitely should ask questions if anything's not clear. And then we need to practice the integration material, the stuff that we're covering now in chapter 6. We need to practice that a little bit more before we get too far into the new material. So I do have a homework assignment for you on that, which will be due again on Saturday. So I apologize for having a couple of weeks here where we've had to do a Tuesday, Saturday turnaround. But this is also not very long. If you start on it by Thursday, I will definitely jump in and give you a hand with it. But I think we need to get that one done well in advance so that we don't have a lot hanging over us before the exam. One thing that I didn't find time to do this time around is to give a quiz. You probably remember for both of the first 2 midterms, we took a quiz. I haven't really figured out if and when I would have a quiz, given that our exam is coming up so soon. But believe it or not, in my SOQs in the past, students have said things like, "Oh, we wish we had more quizzes." And I was kind of surprised by that. But I think it's just because people like to have an idea what kind of problems would they need to be able to answer. So I might write up a mock quiz and just give it to you, or maybe we could do it as an extra credit or something like that. So
I like that.
you like that? Okay. Well, let's think about it. I haven't put one together yet, so I'll try to report back on Thursday if I've made any progress on that. But I may not do it in class just because of, well, the semester is getting very short. I don't know if you realize this. This is the 3rd to last week. We only have like 6 classes left. One of those is going to get eaten up by this next midterm. So next week on Thursday, we do have an exam. I have got that resources folder shaped up now. So in addition to the sample exam that's in there, along with the solutions, there's also a review packet that has a lot of important terminology, things to be able to do, and some additional practice problems. I think there's only like 4 of them. But I also put the solutions to those problems in there as well. So keep that in mind. And I'm going to do some review sessions as well. By the way, the exam is going to cover the last part of chapter 4. So this starts with those applications of continuity, things like the location of roots, the intermediate value theorem, the extreme value theorem, some of those kind of things. Then we have uniform continuity, right? Chapter 5, that was all about derivatives. Okay, everything from the definition all the way to the applications of derivatives. And then we're just getting into chapter 6 right now. We will be done with 6.1 probably by today. If not, we might spill over slightly into Thursday. But the good news here is we're going to have most of this material done well before next week's exam. So you'll be ahead of schedule in terms of learning everything for the test. The review packet has my extra office hours next week. I'm going to try to be around extra for you guys in case you do want to talk to me or just need some motivation to study and we want to come by my office hours to do that. That's great. Review sessions, unfortunately, I was going to do the Wednesday review session like I did, I think, well, I was going to try and push it so it doesn't conflict with your classes at 4 o'clock. I guess this doesn't. But there's a awards night on that Wednesday night, so I can't go late on that Wednesday evening because of that. So I'm gonna do the review before the 4 o'clock time. I think most people should be free between 3 and 4. Of course, this is all optional, right? Is that okay?
Yes,
So,
I can actually go.
okay, so good. So let's do from 2 to 4. It's not perfect, I'm sure, for everybody, but I will record it as always. I will have Zoom turned on if you want to just come in through Zoom. The Monday evening time seems to always have worked fairly well. I've had pretty good turnout on that, so I'm gonna stick with the Monday, 7 p.m. So this is next Monday at 7 o'clock, and then Wednesday from 2 to 4. So there will be another handful of practice problems that I'm gonna be going over with you guys during those review sessions. Of course, everything is optional. The review packet, the sample test. If you could only do one thing, if you only had time to do one thing to get ready for the test, I'd probably do the sample test, because it gives you an idea what kind of questions to expect. I'm hoping, especially if you feel like you need a little extra help, that you might think about trying to either come or watch one or both of those review sessions, or look around in the review packet at some of the other problems that are there. So there's quite a bit to look at. There isn't a huge amount of material for this exam, I wouldn't say. We just had an exam, it seems like, right before spring break. So it's about 5 or 6 sections here. It's not too bad, but yeah, there's still plenty of definitions. I'm hoping you have your flashcards going and that you're recycling them quite regularly to try to get yourself ready for this. But it should be the same format as the last 2 exams. I'll probably let you take something home, give you an extra 36 hours or something to kind of stew over something that you would like to have more time for outside of class. I'll probably do that as well, but I haven't really thought specifically about what I'm going to ask yet, but that's kind of my thoughts on that. Does anybody have any questions? Yeah, Crystal?
So is the final exam, that's the rest of the material covering?
The final will be cumulative.
Well, yeah, but I'm saying, are we gonna be doing that week after?
There will be more to cover, yeah. So we have one more week of class after this one. So May 6th and May 8th, we'll still be in chapter 6. We're actually gonna cover 6.3, 4, and 5 as well. So there's a few more sections. We'll get started on some of that actually this week. But, and even next week on Tuesday, but there'll still be some leftover stuff. Whenever I get done with the fundamental theorem of calculus, which is like the big climax for Math 350, that will be it. And if I'm done early, then we'll start reviewing for the final during class early. And at the rate I'm going so far, there's a good chance I might actually finish a little early with some of this stuff and we'll have time to review. That's my hope anyway. So, good question. Any other questions about this for the time being? Yeah, Ayushi?
So the final, how is it like enough, is it the same like weight as in, or not weight as in the grade book, but the number of questions?
It'll probably be similar in terms of its length because it's also a 2-hour, I think that's right. I think the final is a 2-hour block and this is obviously a 2-hour block as well. I'll have a sample final. So I don't want to inundate you with like the final exam resources quite yet. But there will be a resources folder, you'll see a sample exam and so on, get an idea. But yeah, because of the time frame being about the same, you should expect it should be about the same length, but of course the scope of it will be much more. Probably also for the final, there will probably not be any take-home part. That's actually not my choice, it's really the university. There's a policy about assigning work during finals week. You're not supposed to do it. It makes people do stuff outside of class. So I'm gonna be careful about that. Maybe I could do something up front the weekend before finals or something. I haven't thought about it yet, but I don't wanna, break any rules and get
So you're just gonna let us look at the final, we'll pick what to do before the final.
something like that. Yeah, sounds great. Yeah, I gotta figure it out. I just can't give you work to do outside of class during finals week. I'm not supposed to do that. If any of your other professors are doing that, they're not supposed to be doing that either. But anyway, yeah, okay, so anyway, we'll talk more about the final after we get through this midterm. Try to take the midterm as kind of, you're double dipping on your studying. The stuff you study between now and May 1st, you're not gonna just forget all of that before the final, which is like less than 2 weeks later. So it'll be really good. If you could put some good effort into this, then I think you won't be starting from zero in like trying to get ready for the final. So, it's just kind of the way I look at it. Okay, So, anything else? Good questions. Yes, sir, and Cozy.
Final Tuesday or Thursday?
I think it's on Tuesday.
Tuesday.
I think it's on Tuesday, and I have to remember if it's from 1 to 3. Sometimes they shift it by 1 hour. I can't remember. It's in the syllabus. I looked it up weeks ago, but it is on Tuesday.
Okay.
Yeah,
It's on Tuesday from 1 to 3.
Tuesday from 1 to 3. Probably I will be doing some review sessions. Because it's a Tuesday exam, I think most of my midterms have been on Thursdays. If the final's on Tuesday, I'll probably do review sessions the weekend before. Either Saturday or Sunday, and then maybe also on Monday, but I haven't thought that far ahead yet. I can only keep one exam in my head at a time, so that's the best I can do. Okay, well, with that as a overview of where we're at, I put a fairly big recap on the board over here, guys, and that's because this notation for setting up Riemann integration is fairly extensive. So let's just remember what it was all about. I'm going to try to keep this on the board as well. I'm going to try not to erase over here too much today. So the set of partitions of a closed interval, if I imagine a closed interval from A to B, then the partitions those are just ways of chopping up that interval from A to B. And I have x0, x1, x2, x3 up to xn as my partition. The set of all of those partitions is script P, and we can take a specific partition in that set and call it P. Okay, so P is our usual notation for a partition. The width of each of my subintervals is going to be an important notation. You're going to see it here in a minute, and that is delta xi. So for each of my subintervals, I have a width, which is obtained by just subtracting the next point from the previous point. Okay, just find out what that distance is between those points. So that talks about the partition of my x-axis, right? So somewhere here I have my interval from A to B, and I've just chopped it up somehow with these xi's and created these subintervals that collectively fill up the entire interval from A to B. Okay, but in addition to the sort of looking at how the domain is broken down, we also have a function here, which is f. So f is some function, and the only thing that I have assumed about my function up until this point in the discussion is that it is bounded. I have not even assumed that it's continuous yet. So it's not anything special, but it does need to be bounded. That just means it does not go off to infinity or minus infinity. If I was to graph the outputs, they would be somehow bounded. I could draw two horizontal lines across my whiteboard there, and the function would stay between them. It's possible to do that. That's what it means that we have a bounded function f. Right, okay. Then we had the big MIs and the little mi's. These are just sort of the maximum and minimum values of the function on the ith subinterval. So for each subinterval, I just look what's the largest value of f of x and what's the smallest value of f of x. Those are going to be denoted with capital M sub I and little m sub I. Obviously, I put this little note here. This is kind of obvious, but I wrote it down anyway. Little m sub I is always less than or equal to capital M sub I, because your infimum of the same set is less than or equal to the supremum of the same set. So that's pretty clear. And so then we can define the upper and lower sums relative to the partition P, or with respect to the partition P. So U of PF is simply adding up the rectangles that have a width of delta xi and that have a height of either capital MI or little mi, depending on whether I'm talking about the upper sum or the lower sum. Okay, so we have each one of these that we can write down for every partition. So everybody in this room, we have 15, 20 people in here, we could get 15 or 20 different values for U of PF and L of PF, depending on which partition you personally chose to use, right? So for the same function and the same interval, we can get lots of different answers here for the upper and lower sums because it hinges on what the partition is that we're choosing. Okay, well, what we ultimately wanna do is define the Riemann integral of f on this interval AB. But the first step is to talk about the upper Riemann integral, right? And then the lower Riemann integral. And here are the notations for those, so you're gonna need to know these. I either put an overline or an underline on my integral notation. And for the upper Riemann integral, I'm gonna take the infimum of all of the upper sums. So this is a massive number of, because you have a massive number of partitions, so you have a massive number of upper sums, it's an entire set of values. And what you're gonna do is take the greatest lower bound, which is the infimum of all of those upper sums. And that is called the upper Riemann integral. Okay, it's a little weird, it's an upper integral, and yet you calculate it by doing an infimum, which always feels like it's a smaller thing. But you're taking the smallest of, essentially you're taking like the smallest of all of these overestimates. The UPFs are all going to overestimate the actual value of the integral. You're gonna take the smallest of them, the infimum of those. Right. Okay, and flip this whole concept on its head and you get the lower Riemann integral, which is just the supremum of all of these LPFs. The LPFs are all going to underestimate the actual value of the integral. So you're gonna take the largest one. This is the largest of those lower sums, which are all underestimating the value of the Riemann integral. Am I saying that right? Yeah, so, I mean, it's, the supremum is the least upper bound of this set. So you're taking something that is an upper bound for this set of values, and you're taking the least of those. Okay, so that's how this is set up. Question?
I don't wanna jump the gun, but how do you prove like a Riemann integral is equal to some more given?
I don't think I quite follow your question. So far we have not defined the Riemann integral. We've defined the upper Riemann integral and we've defined the lower Riemann integral. Ultimately, I need to define the overall Riemann integral. Okay, so that's still coming. We haven't gotten to that yet. But you know, you have learned how to find infimums and supremums of a set. So it is possible that we could do some examples. In fact, I'd like to start with one today. An example where we can calculate the upper Riemann integral and the lower Riemann integral. So yeah, let's do that, guys. Let's do an example over here. I think I'm gonna come back over to this side and try and do a quick example. That sound good? Yeah, I see that, thanks. So here's an example. So I'm going to make a really easy example. F of x is going to equal 1 if x is in Q, and 0 if x is not in Q. And I'm just gonna let the interval I be any interval from A to B. It's not really going to matter what the interval actually is. And what I'm gonna try to do here is I'm gonna try to compute the upper and lower Riemann integrals. So let's compute the upper Riemann integral, which is the one with the over bar on it. And let's also compute the lower Riemann integral. Okay, so I'm going to try to do this. Okay, so for the solution, for either one of those calculations, I have to calculate for every partition, I have to calculate the upper sum or the lower sum, right? So let's just look at a partition. Okay, so let's let P be in the partitions of the interval from A to B. And for each of these subintervals, So each of the subintervals would be an interval from xi minus 1 to xi. Can somebody tell me for each one of those, now notice I'm not being very precise about what the partition is. I've just said let P be some, so you just have some chopping up of this interval from A to B. But we don't have a specific one in mind here. But I claim that even though I didn't really get very specific about what the partition is, I think we should be able, excuse me, we should be able to tell what are the capital M's and the little m's. What do you think the capital M sub i's are going to be? What is the supremum of the f of x values on any one of my subintervals? Here's my function. Would you guys agree that on every subinterval, there's gonna be a rational number somewhere? And there's gonna be an irrational number somewhere also? Yeah, so the capital Mi is always 1. And what will the little mi be? What's the infimum value on that closed subinterval? 0, absolutely. Okay, and so that's for each of my subintervals, right? So thus, it actually doesn't matter what the partition is. If I wanted to calculate UPF, let's just work it out. UPF is the summation from I going from 1 to n of capital Mi delta Xi. But all of my M sub i's are equal to 1, guys. So this is just the summation of all of the delta Xi's. So the M sub i's are all 1. And what do I get when I add up all of the delta Xi's? I add up all the widths of all the subintervals and kind of glue them all together. What do I end up with? The entire interval from A to B, which would be a distance of B minus A. Exactly, so this has to be B minus A. So that's the UPF. And while we're at it, let's do the LPF. So this would be the summation of little mi delta xi, excuse me, little mi delta xi, but all of the little mi's are 0. So if I just keep that in mind, then I'm just adding up a bunch of zeros here. It turns out it doesn't matter what the partition is. This is LPF, it's always 0. And UPF is always B minus A. So my sets that I'm taking the infimums and supremums of over here, let's keep this in mind. I hope you guys can see this okay. This is super important definitions, right? So thus, the upper Riemann integral of f, which is the infimum of all of these values. Well, when I say all of these values, this is the same value over and over and over again. So the infimum is just that value, B minus A. And the lower Riemann integral, which is the supremum of all of these lower sums, the supremums of all these values is just 0, right? It is just 0. So those are your answers. They are not the same. Is everybody with me? Okay, so that's a pretty easy example. So by the way, these two estimates, these upper Riemann integrals and lower Riemann integrals, do not have to be the same. That's the first thing that I want us to get out of this example. They do not have to be the same. However, they are related to each other. And in some cases, they will be the same. So we're going to talk about that as we go a little bit further. You can tell this is not a very nice function. Right? It's not continuous anywhere. It jumps back and forth between 0 and 1 all the time. Even on a microscopic subinterval, it's going to do that. So it's not a very nice function. And so we shouldn't be too surprised that we don't get consistency here either. But let's see where we can go with this. I am actually going to prove that this lower Riemann integral is always going to be less than or equal to the upper Riemann integral. Less than or equal to. But in order to prove that, I first need to talk about something called a refinement. So I'm going to talk about a refinement of a partition. So I have a definition for you here, guys. This is definition 6.3. And here it is, we call P star, I'm gonna use a star on this. We call P star a refinement. It is called a refinement of P if P is contained in P star. It's a pretty simple definition. So if I have a partition P where I've chopped up my interval from A to B, what P star would be is a superset of P. That just means you would have added some more tick marks. Right? So the refinement has more subintervals, it's chopped up into more pieces that are smaller than the partition that you had originally, okay? So just as an example of this, you know, we could have the partition P could be, I don't know, 0.5 and 1 on the closed interval 0 to 1. So that might be the original partition, and then if I want to refine that, all I have to do is throw in a few more points, so. You know, maybe I throw in a quarter, and then I have a half, and then maybe I throw in 0.6 and 0.9 and then 1. So this is a refinement, it has all of the points that the original partition had, but now it has some additional points as well. Okay. Great. And then I'm gonna make a little remark here, and this is also very short, so I think I can squeeze it right here. If you start off, my friends, with 2 partitions of an interval. So if I have 2 different partitions from A to B, I've chopped it up in 2 different ways. A natural way to refine both of them simultaneously would be to just take their union. Just take all of the common points for both partitions and throw them together. So a union of 2 partitions is naturally a refinement of each of those individual partitions. Let's write that down. So if P1 and P2 are partitions of some interval, let's say AB, then if I start with that, then I can form P star as the union of those 2 partitions. So P1 union P2. And this is a common refinement. It's kind of a common refinement of the individual partitions P1 and P2. So we're gonna use this idea in a minute. That's why I'm putting this remark here. We're gonna need this idea that we can take 2 partitions and we can refine them by just taking their union. Lizzie?
Is it the current bracket turned into a regular bracket?
Cause I'm being silly. That should probably be a braces. Yeah, thank you. Yeah, good catch. Any other questions so far? Okay, well, guys, with that in mind, I am ready to state a proposition here. This is Prop 6.1, and what it says is that if P star is a refinement of P, then L of PF will be less than or equal to L of P star F, and U of P star F will be less than or equal to U of P F. Now, let's remember that the upper and lower sums, the upper sum is sort of an overestimate to the exact area under the graph of f of x. And the L of PF is like an underestimate for the correct area under the curve. So you can see that if you perform a refinement, look at what is going to happen. Your overestimate is going to come down a little bit. means it's gonna get better. It's gonna be closer to the right area. And your underestimate is also going to improve because it's gonna increase a little bit. Again, these two lower and upper estimates are now closer to each other with the refinement of the partition than they were originally. So performing a refinement of your partition can only help you. It can only bring these lower and upper estimates closer together to each other and to the right answer, which is kind of somewhere in the middle, right? Which is the way that we normally think about these things happening. Okay, so let's, this is definitely instructive to look at the proof of this. So I'd like to do that. The book does the L case. So the L case is done in the book. So usually on something like this, I like to do the opposite one to the one that's in the book. So I'm gonna do the proof of the U case so that you have something different to look at. So let's get started with the U case. So we prove the U case. In the notes here, we'll do the U case, and then you can look at the book if you want to see the L case. But the idea is, let's start with our partition P. So P is going to be the set X naught, X1, X2, and dot, 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 up to Xn. So we start with our partition P, and what I'm going to do is I'm going to refine that partition now. A refinement is just any superset of P. I'm gonna imagine that I only am going to refine it by putting one more point into this set. Because of course I could repeat that iteratively several times, but I'm gonna imagine for the moment that P star just has one extra point in it. So namely, that P star is P union with Z. So I'm gonna throw in this point for some Z with xk minus 1 less than Z less than xk. Okay, so in other words, what we're saying here is that P star starts out at x naught, x1, and dot, dot, dot. We get all the way up to xk minus 1. And then the next element in the partition is Z, and then we get to xk, and we continue on as normal to xn. So we're throwing in one more point somewhere in the middle of our partition, and that's P star. I'm just gonna try to convince you that if I do this, if I throw one more point into my partition, then my upper sum is gonna come down from what it was originally. That's all I have to prove here. So far, so good? You following? Okay, well, let's look at it. So let's look at the U of P star F. Let's see what we can say about this one. Obviously, I'm gonna have a bunch of terms here, summations, but I wanna do, so the terms are gonna be capital Mi delta Xi. But I don't wanna do the case term right here. So I'm gonna say for I not equal to K. So we'll start off, because the first subinterval is the same as it was for P. The second subinterval is the same as it was for P. The only one that's screwed up a little bit is we have this subinterval from xk minus 1 to xk, which we've now split into two parts. So I'm not done yet. What I'm doing is I'm sort of saying all of those other subintervals, leave them the same as they were before. And then there's two more subintervals that have been created by this Z that will replace the one missing term here that we've excluded. And let's write down these two other terms. I'm gonna call this M prime, I'll write down in a minute what that means, times the width of that subinterval, which is Z minus xk minus 1. And then there's one more term, which is M double prime times xk minus Z. Okay, so this is the formula, and this is where, let's write down what M prime is and M double prime. M prime and M double prime. I need to write down what those are equal to. Those are just going to be the supremums of the function f of x on the little subinterval that I've now created. So in the case of the first one, xk minus 1 less than or equal to x less than or equal to z. And in the case of the second one, which is the M double prime, we're talking about the supremum of the set of f of x, where z is less than or equal to x is less than or equal to xk. There we go. So far, so good?
Yeah.
Yeah, not too crazy. Guys, all I've done here is I basically said that this z creates two sort of special subintervals. And then all of the other subintervals are just the same as they were with the original partition P. Right? So what I want to have us note here, I want to note that both mi prime and mi double prime, both of those supremums. Now remember, these are supremums on the little subintervals that were created by z. Would you agree that those individual smaller supremums would be less than or equal to what would have been the supremum of the kth subinterval of the original partition? Because now this bigger subinterval that you had before would have had a bigger supremum value because you've got more x's in that subinterval. So this is less than or equal to the m sub k that would have been there for the original partition. Okay? So thus, that's actually the whole idea of the whole proof. That's the whole thing right there. The rest of this proof is nothing. Basically now I'm gonna do u of p star f. And I'm gonna say that it equals the summation I not equal to k of m sub I delta xi plus capital M prime times c minus xk minus 1 times capital M prime times xk minus z. So I've just recopied the same thing that we had written a moment ago, but I'm now going to replace the M prime and the M double prime. I'm going to replace both of those with MK. So let's leave the first term the same. I not equal to k, m sub I delta xi. But now I'm going to replace M prime with M sub k, z minus xk minus 1. And then I'm going to replace the M double prime also with k. So I'm just replacing the M prime and the M double prime with this larger supremum. It's larger because it's the supremum of the entire subinterval that has been chopped in two. And guys, if you factor this m sub k out of these last two terms and then simplify the part that's in the parentheses, let's see what you're left with. If you factor out m sub k right here, then what you're left with is this parentheses plus this parentheses. Do you see that the z's cancel? The z's will cancel, and what are you left with? Oh, xk minus 1, which is just delta xk. So in other words, this whole thing is just the summation of all of the mi delta xi's, I going from 1 to n. That's u of pf. That's u of pf. There's your whole proof. That's the whole thing. So there's nothing terribly deep about that. Nothing too crazy there. Okie dokie. Any questions there? This is a really important result when you refine a partition. You improve the upper estimates by making them smaller, and you improve the lower estimates by making them larger. Okay. Sweet. Well, now I've got another proposition for you. You ready? This is actually, I have to tell you, this is my favorite chapter of the entire class. I know I say it whichever chapter we're on is like always my favorite. I really do love this part. The way Riemann integration is done, it's a beautifully developed theory. And it's tying together a lot of things we had to study earlier, right? Supremums and infimums, sort of that kind of analysis. And so I just really like this stuff. So I'm trying to be as excited as I can without getting myself into a coughing fit or something. So hopefully you're getting a little bit of that out of this as well. Okay, so here is the next proposition. If P1 and P2 are partitions of the closed interval from A to B. Okay, so if we take two partitions, now these two partitions might have nothing to do with each other, but then the lower estimate using partition P1 of F is always less than or equal to the upper partition using P2 and F. Now, if you try to understand that result without thinking about it too hard, you might be thinking this is obvious, because isn't it true that the lower sums are always less than or equal to the upper sums? The lower sums are based on these little mi's, the upper sums are based on the capital Mi's. But if we were using the same partition, I would completely agree with you that it is obvious that LPF is always less than or equal to UPF. But here we've started with two partitions that have nothing to do with each other. We might have chopped up this interval from A to B in one way to come up with the LP1 of F, and then we might have scrapped that and said, I'm gonna start over by chopping up my interval a completely different way, which means that my big M's and little m's could be completely changing when I change partitions. And we're gonna look at that upper sum. It turns out that even if you scrap your first partition and replace it with a completely different partition, a lower sum will always be less than or equal to an upper sum, no matter what the partition was for the lower sum or what the partition was for the upper sum. All of these numbers are always less than all of these numbers. Okay, so if you just glance at it really fast, you might look at it and say, oh, that's obvious. But then when you pause for a second and say, wait a minute, the partitions are not the same. They might not be the same partition, so it's not maybe totally obvious that it's true. Now, having said that, this is a one-line proof. So this is not a hard proof. And so you'll see right away that there's not a lot of depth to this. Because what do you suppose I'm going to do with the two partitions? I don't know that they're equal. I can't say that again. How about make a refinement, right? I don't know that the two partitions are equal, but given two partitions, P1 and P2, we can always form a common refinement. And that's exactly what I'm going to do. I'm going to let P star be P1 union P2. Then what we can conclude is that L of P1 of F is less than or equal to L of P star of F. So this is where we're using prop 6.1 right here. So L of P1 comma F, be sure your ones and your commas are not getting mixed up here. L of P1 comma F is less than or equal to L of P star with F. And then as long as I keep the partition the same, so I'm going to continue to use P star, as long as I don't change the partition, a lower sum is always clearly less than or equal to an upper sum using the same partition, right? But then U of P star of F is less than or equal to U of P2 of F, and here we're back to proposition 6.1 again. So that is your entire proof. That is your entire proof. So any lower sum will always be less than or equal to any upper sum. And the glue between the two partitions is their common refinement, which is their union. Okay, great, so that's the proposition that we need to now get to our first big theorem of this section. Which is that I'm now gonna try to prove for you that the lower Riemann integral of f is always less than or equal to the upper Riemann integral of f. This is a theorem. This is a theorem. Okay, so let's put a box around this equation. This is the theorem, and I'm gonna maybe come over here to write the proof of it. The proof here is also gonna be pretty short. We know that every upper sum is always more than every lower sum. So it seems reasonable that the upper Riemann integral should be greater than or equal to the lower Riemann integral. Because all of the things in this set are greater than all of the things in this set. The issue is though, that you're taking an infimum here. Ooh, so now you're talking about something that's actually a lower bound for all of those numbers. It's the greatest lower bound, but it's a lower bound. So you're taking a lower bound for all of these values. While down here, you're gonna take an upper bound for all of these values. So even though these values are always less than all of these values, if you take the infimum of these values and compare it with the supremum of all these values, now suddenly it's maybe not 100% clear that the upper Riemann integral has to be more than the lower Riemann integral, and so we have to have it as a theorem that requires a little proof. So I am going to do that for you. I'll show you the proof here. It's really a nice proof. So here is a proof. And what I'm going to do is I'm going to fix a partition. I'm going to call it P1 of the closed interval AB. Okay, now by the proposition 6.2. So this is just any old random partition. By proposition 6.2, the L of P1F will be less than or equal to every upper sum on the planet, right? It will be less than or equal to all of these. So let's write that down. L of P1 of F. Actually, doesn't that mean if it's less than or equal to all of these upper sums, doesn't that mean it's a lower bound for the set of all of those upper sums? It's a lower bound, right? So it is a lower bound for the set of all of the upper sums, all of the UPFs, where P is just any partition. It's a lower bound for all of those upper sums. But guys, the upper Riemann integral is the greatest lower bound of all of the upper sums. So I can compare this lower bound with the greatest lower bound, right? So thus, the L of P1 of F is less than or equal to whatever the greatest lower bound of all of those sums is, which would be, as we have in the definition over there, the upper Riemann integral. Okay, so just have to remember, this guy right here is the infimum of all of the UPFs. It's the greatest lower bound of all of the UPFs, but here is another lower bound of all of the UPFs. So comparing the two, the greatest one is this one. It's greater than or equal to any other lower bound for all of the UPFs. But I'm now going to flip this on its head, and I'm going to say, well, this guy is an upper bound for this, and P1 was arbitrary. I could switch that partition to any other partition, and I could still say that L of any partition with F is less than or equal to this guy. This guy, therefore, so let's just say that, let's write that down. since P1 is arbitrary, right? And this upper Riemann integral is greater than or equal to L of P1F, right? Then that means that this guy here, the upper Riemann integral, is an upper bound for the set of all of the LPFs such that P is in script P. All right. Great. Well, it's an upper bound for all of the LPFs, but guys, the least upper bound of all of those LPFs is this guy. This is also an upper bound for all of the LPFs, and this is the least one. So this one had better be less than or equal to any other upper bound for those LPFs. Okay, so hence, by definition, this lower Riemann integral, which is the supremum of all of the lower sums, in other words, it's the least upper bound for all of those lower sums, has to be less than or equal to any other upper bound for all of those sums. So there you have it. Honestly, the thing that drives this proof is just knowing what sups and infs are. You have to understand the concept of a greatest lower bound and a least upper bound. And then the proof flows really nicely. I'm pretty sure this one is in the list of theorems to make sure you know how to do next Thursday. In the review packet, I have some double stars on theorems or results that I think are doable on the fly, meaning that I would hope students could, having studied enough, be comfortable with proving them. So this one is, I'm pretty sure it's on that list. Yeah, it is. Okay, sweet. Let's make just a little more progress, then we'll take a little break. But I've got some really important results on the board. Probably on Thursday, I'll come in here and write them all down again. We've got the fact that a refinement improves both the upper and lower sums. We've got the fact that every lower sum is less than or equal to every upper sum. And now we have that the lower Riemann integral is always less than or equal to the upper Riemann integral for any function whatsoever. Okay, so now I'm ready. I think we have sufficient motivation for a definition. And let's see if we can make sense of this. I'm going to let f from the closed interval AB to R be bounded. So take a bounded function. This is really where it's all been building to, guys. This is the biggest definition of this chapter. What does it mean to say that f is Riemann integrable? So we say f is Riemann integrable f is Riemann integrable, and we should maybe, if it's not clear, we can always emphasize what the interval is that we're talking about, because sometimes it could be Riemann integrable in one place, but not in another. F is Riemann integrable on this closed interval if the lower Riemann integral, which is the supremum of all of the lower sums, is actually equal to the upper Riemann integral, which is the infimum of all of the upper sums. So if the two numbers are actually equal, so we know that the lower Riemann integral will always be less than or equal to the upper Riemann integral, but if they're equal, then f is Riemann integrable on AB, and its common value is denoted just as the integral from A to B of f without putting an underline or an overline on it. Okay, so that's That's great. So if the upper and lower Riemann integrals are the same, then the function is Riemann integrable and we can just drop the bars, basically. Okay? And then just a notation that kind of goes along with this definition. I'm going to let script R, or if it's not clear for sure what the interval is, we could always include the interval there, so script R of AB. I'm going to let this denote the set of Riemann integrable functions. The set of Riemann integrable functions on the closed interval AB. Okay. So any function that's Riemann integrable will belong to that set. And erasing a little bit of this, I want to try to keep this box over here. So we can keep referring to the upper and lower Riemann integrals. Do you have a question there, Ishi? Why do we need to denote that set? We don't have to, but we're going to use it. It's just a handy notation to have. So I'm going to want to have that to use. But yeah, you wouldn't need to. Yeah. So any function that's Riemann integrable belongs to this set. I mean, one of the main goals, guys, of the rest of chapter 6 is going to be to figure out what kind of functions are Riemann integrable. And so having that notation will allow us to state theorems nicely and pretty easily. We're going to want to decide whether a function belongs or does not belong to script R. Is it Riemann integrable or not? In other words, do the upper and lower Riemann integrals agree or not? So I'm going to state one more theorem here. This is the theorem that you're going to be using, or that we're going to be using to do those homework problems from today's homework, as well as for Saturday's homework. This next theorem is hugely important for the rest of this semester. So I'm going to state it here. This one I don't think is on the double star list because the proof is a little longer, but the result itself is probably more important than any other result we've had so far today. So let's write it down. As always, let f be a function from the closed interval AB to R, and we're going to let that be bounded. Then, just to sort of prove my point with Ayushi, I'm going to use the notation right away. F is an element of the Riemann integrable functions from A to B, if and only if. Look at this, guys. Look at this. I'm going to get a characterization right now. And if and only if characterization, this is a characterization for when is my function Riemann integrable. When will this be the case? Because honestly, to check that my function is Riemann integrable, I don't want to have to figure out the supremum of all of the lower sums and then figure out the infimum of all of the upper sums and see if they're the same every time. That's a lot of work. We don't want to do that. That is too much work. Checking this is not a fun thing to want to do, right? Checking, I mean, even calculating this number and calculating this number are not usually very easy. I know I did the one example earlier today where it was easy, but for most functions, it's not that easy to calculate this thing. So let's avoid having to do this by coming up with a beautiful theorem that will tell us when these two numbers are going to agree. And it's a very nice theorem. And how could it not be nice? It starts out with for all epsilon greater than 0. So if we see that, we're like, yay, this is math 350. This is what we always talk about in this class. For all epsilon greater than 0, there exists not an n naught, not a delta, but a partition. There exists a partition P, which is in the script P of AB. There exists a partition of that interval with, and now here's the key equation, UPF minus LPF is less than epsilon. Okay. So what is so nice about this condition is that to prove that f is Riemann integrable, I don't have to go calculating all of the upper sums and all of the lower sums. Just starting with an epsilon, I have to find one partition. I only need to find one. I have to construct it. I have to figure out how do I want to chop up the interval AB. I have to construct that partition such that the difference of these two numbers is as small as I want, right? For all epsilon greater than 0, I can create this partition. You see? This is the idea. And I'm going to, before we'll take a 10-minute break here, but let me give you a little bit of a notation here that can be helpful, which is, you might wonder, well, how are you going to describe this partition in terms of epsilon? I mean, it's a little bizarre to think about doing that, but we can do it a little easier by converting the epsilon sort of back in terms of natural numbers again. So if we let little n be a natural number, I'm going to define P sub n, which is in the partitions of AB, via x sub k equals x naught plus b minus a over n times k. So, guys, what this is doing, what this is, if you're wondering what is this partition, because you're going to want to use this partition quite a lot. What this partition is, remember you start at x naught and you end at xn. What this partition does is it starts at the left endpoint and it chops up b minus a into n pieces that are all the same width. They're 1 over n of the full width, right? And you're literally chopping it up into equal sized subintervals, right? So this right here is b minus a over n, and then this is also b minus a over n, and this is also b minus a over n, and so on and so on. They're all the same width. And what that allows you to do is, instead of searching for some kind of hard to conceive partition P, I've already given you infinitely many good candidates right here. P1, P2, P3, P4, these are special partitions where you've chopped up the domain into exactly a bunch of equal sized subintervals. Is everybody with me on this? So if I had n equals 3, if n was 3, then we would be chopping it into 1, 2, 3 equally spaced pieces. And when you're trying to come up with this, if you're trying to use this theorem and you're trying to come up with a partition, you could come up with one of those, which is indexed by n. And if it's indexed by n, that's natural numbers. I can deal with that a little bit more easily than just kind of abstractly trying to create the partition. So we need to prove this theorem, but even more importantly than that is going to be to use it to do some problems. So let's take a break, and when we come back in 10 minutes, we'll look at the homework problems, and then if there's time left at the end, I'll try and prove this theorem today. Otherwise, we'll prove it on Thursday, but this is one to go right onto the top of your pile of flashcards. Super, super important result. So at about, 2:15, we will pick things back up again. Feel free to stretch your legs in the meantime, though.
Is there a restriction on F that F has to be continuous?
That's the beautiful thing. It does not have to be continuous here. It will turn out that if f is continuous, it will be a Riemann integrable, but that assumption does not get used anywhere so far in this theory.
So, closed interval of A to the interval B is P one. And then B, close to B, close to C is P two.
Uh-huh.
This interval equals one. This interval equals two. How is the lowest of that one bigger than the highest of her? What is it?
Oh, these are partitions of the same interval. Same interval A, B. So we're not going from A to B and then from B to C here.
Understand that, like, if you break that up in that interval, then it's, the middle of it's broken.
Oh, the function? Yeah, that can happen.
So,
Yeah, I'll talk about this for a couple minutes. If we can't get this sorted out now, I'll have to do it later, because I've got to give myself a break. But so if the function is something like this, and then like this, you mean?
yeah, and then,
So
so,
wait.
let's say, call it P one, P two, whatever.
So P1 has to be a partition all the way across, right? And then P2 is maybe some different partition all the way across. So you have two different partitions of this interval. In the context of this
We're at
proposition,
the same AB.
yeah,
Okay,
that's what you need, okay.
I was, to me, a partition is one part, it's a slice of the pie.
No, this is a partition of the full interval from A to B. Yeah.
Thank you.
There is gonna be a homework problem for Saturday where you prove that if F is Riemann integrable from A to B and also Riemann integrable from B to C, then it's also Riemann integrable from A to C. You're gonna use this theorem to prove it. And there you are going to have to sort of merge two different partitions of two different subintervals together.
And that's closed.
Yeah, they're always closed.
Okay.
Yeah, they're always closed.
So they hit each other.
That's right, that's right.
Thank you, that was
Sure.
breaking my head there.
No problem.
Kind of missed the rest of the lecture.
Oh, no.
Be fixated on one thing.
Yep.
Don't hesitate to ask at the time. If you think of something in the moment, because might just be that you're not the only one wondering.
Okay, I have a question actually. So we're doing a proof for the utilities. And we said, okay, so then our Z cancel out, our NKs get factored, we'll have to see what it means.
Well, it's just xk minus one, so that becomes another one of your, that's a delta xk, which coincides with the kth term of that summation.
Okay.
Yeah, so that's where that went. Yeah, good question.
On these,
Yeah, sure, but. Right,
there's a lot of,
this will be.
at TV too.
Oh, it's crazy.
I eat that free barbecue password lamb.
When,
What?
oh, you tried it? Last week?
Did you have, you had the lamb?
No, but.
No, it's good.
Oh,
Cause you know, password lamb.
oh, yeah. I thought they.
Very good lamb.
A couple times.
Very good.
I heard that they started by moving it smell like spice.
I don't remember what's it's been a while. Pastor, you crazy? Sometimes when I get ready in the pastor. I should have got this crazy stuff. Like. Like a massive curse. You know, it's like the curtain ripped in two. You know, like the curtain ripped in two. The curtain. Then we had like. Last year we had bricks.
Mhm.
No, last year was going bricks. And it's like write your sins on it. Like throw it on the cross because Christ took your sin. And throw the bricks. And then last year we had
Just break the bricks.
break, we throw them on the cross. Yeah. And last year we had a pastor, he preached the whole sermon, he's carrying the cross. And he could healing a fever. No one else become like 2x4s. Like I carry a cross.
So like every different bands.
Yeah, next year we're gonna sacrifice a cow during the service.
What?
No, I'm just kidding. If we did this, I would be 100% for it. I would be crazy. You would just go.
Do you guys see they're gonna start charging for parking on weekends?
All hours.
I was, for 23 years being here, I was like, it's amazing that they let people park here from Friday night till Monday morning. Almost half the week, like it's a giant free parking lot for the whole, Fullerton.
I saw that and I was like, wait a minute, I misread it thinking they were getting like a wait, they were doing away with the student permit parking.
No, they're still doing
Then I don't
that.
really care, cause I'm.
Yeah, if you have the permit, it won't matter.
Yeah,
Although I kinda like on the weekends sometimes to like pull up to a loading zone somewhere and just throw my car there. And I think next year, because I guess they're gonna have to hire people to like patrol it now.
mhm.
So all this extra money that we're paying for this will
Go right into.
go right into that, or the people who get the permits on the weekends will contribute to that, but anyway, it's weird.
It's revenue.
It's revenue, but they got more expenses too, so I don't know.
But it's also
Do the
like,
economics of it.
they do like performances and stuff after hours, and so it used to be like you could just come
I know, that is
for the
gonna
after
be,
hours.
maybe that's probably what they're thinking.
That's-
Oh, there's a concert Friday night, oh, let's get,
Mhm.
$5,000 of
The
parking fees
movies
or
and
something.
stuff, yeah.
It could be, that very well could be. Anyway, guys, why don't we go ahead and let's get back down to business here. Yeah, so I've kept the definition of Riemann integrable on the board here. And I've just produced this is a huge, really exciting theorem that says that your function will be Riemann integrable if and only if, for all epsilon, you can find a partition such that UPF minus LPF is less than epsilon. The downside of this theorem though, do I have to give you a downside? I guess I do. This theorem does not produce the value of the integral. This theorem only tells you that yes or no, your function will be Riemann integrable, but it does not actually give you the value. So on problem number 1, so let's take a look at the homework problems now that I promised I would go over with you guys. This is a very simple function. I'm gonna even draw a little picture of it here. F of x is just equal to c. Right? So there's my there's my function. And you can see that there's two things that they're asking you to do. One of them is to show that f is Riemann integrable. The other one is to actually find the value of the integral. Guys, this notation here, this notation would not have made sense unless we first know that f is Riemann integrable. So this notation, as you can see, I put it right here, this common value, right, is only going to make sense if the lower and upper Riemann integrals are the same. So we have to kind of do these parts in order. We have to show that it's Riemann integrable, and we also have to evaluate the integral. I am going to do this one without using theorem 6.2, because if I use theorem 6.2, that'll show the first part very easily. But I still have to do the second part. So I think I can show both parts together a little bit more easily. So let's see how we could do this. So for the solution, see, what should be in your mind right now, guys, is that for a constant function, it does not matter what the partition is at all. The partition will not matter in terms of the capital M's, the little m's, the UPFs, the LPFs, and the infimums and supremums of those. That it will not matter whatsoever. I'm just going to say let P be an element of the partitions of A and B, of the interval A, B, be arbitrary. So this could be for any partition. For any partition. And in this case, for this case, all of my capital MI's are equal to what?
See,
C, right? Because your f of x values are all equal to C. And what are all of your little mi values equal to? Also to C, right? So capital Mi equals C equals little mi. This is for all I. So if we wanted to calculate UPF, this was the summation. I goes from 1 to n of capital Mi delta xi. But all of my capital MI's are just C. So I can just pull those out as C. And then we just have the summation from 1 to n of all of the delta xi's. And if I add up all the delta xi's, what do I get? The entire interval from A to B, right? So this is C times the quantity B minus A. That's for every partition. And L of PF, of course, will be all the same stuff, right? I'm just writing down the formula for the lower sum. Little mi delta xi added up from I equals 1 to n. And again, we can pull out the C. And we're going to get C times the summation of all the delta xi's. And we're just going to get the same thing again. C times the quantity B minus A. So here's the deal. I'm going to finish the proof. C times B minus A. That was equal to LPF. We just calculated that. Now LPF is just one of my terms that I'm then going to take the supremum of. The supremum is the least upper bound of all of these LPFs. So this LPF would be less than or equal to the supremum of all of the LPFs, which is the lower Riemann integral. Put an underbar on that. And then we have theorem 6.1, which we did before the break, which says that the lower Riemann integral is always less than or equal to the upper Riemann integral. The upper Riemann integral, what is that again? That's the infimum. Still got it on the board if you need to cheat over here. The upper Riemann integral is the infimum of all of the upper sums. In other words, it is a lower bound. It's the greatest lower bound of all of the upper sums. It is less than or equal to all of my upper sums. But what does UPF equal? C times B minus A. Oh. Well, look where we started and look where we finished. This thing is less than or equal to something, less than or equal to something, less than or equal to something. Oh, is equal back to itself again. What does that tell you about all of those inequalities in the middle? They're all equal signs, right? They all have to be equalities, right? So thus, they're all equal signs. So C times B minus A is equal to the lower Riemann integral, which is equal to the upper Riemann integral. They're all the same. And that's the definition of Riemann integral. And the common value is just the regular integral. So we're done. F is an element of the Riemann integrable functions from A to B. And the integral from A to B of F is equal to C times B minus A. There's the rest of the proof. So we just figured out how to find the integral of a constant today, guys. You can go impress all of your friends. They may not be that impressed, but you can say you can actually prove it rigorously. You don't have to just kind of draw a little rectangle and deduce it from that. That's number one. Is everybody good with that? Okay, no questions. Okay, let's do the other one from the homework from this section. I think it was number 4.
Yeah.
Give myself a little more room here to write out number 4. So I've got the question here. So let's look at 6.1 number 4. 6.1 number 4. Okay, so this one has a piecewise defined function. Let me write it down. Let f of x be defined as follows. It's going to equal 1 if 0 is less than or equal to x is less than 1. And then it's going to equal 3 if x equals 1. And then it's going to equal -1 if 1 is less than x is less than or equal to 2. And the question is, show that f is an element of the Riemann integrable functions from 0 to 2. And they also want us to calculate the integral and find the integral from 0 to 2 of f. Okay. So put this over here. Sweet. It might be nice to draw a picture of this function before we get too deep into it. So let me just draw my interval from 0 to 2 here. And here's 1 in the middle. The function has a y value of 1 from 0 all the way to 1. And then there's an open circle at the endpoint on the right. And then f of 1 is actually equal to 3, which is up here somewhere. And then between 1 and 2, we have an open circle at -1 at a y value of -1, and it goes all the way to the other endpoint here, like that. So this is your function. Obviously, it's not continuous. We've never said anything about requiring our functions to be continuous in this section. So that's fine. We apparently are still going to be able to prove that f is Riemann integrable, and we're going to be able to find the value of this integral here. So I think this time, what I might do is I would like to show you the power of this theorem, and I did not use it on the first example, so I think I'm going to use it here, but I just want to reiterate again, this theorem will be great for showing the first part, right? F is Riemann integrable, if and only if. It'll be great for this first part. When we get around to wanting to evaluate the integral though, we will have to do something besides just looking at this theorem. Okay, but let's do this one in 2 parts where we can kind of see the power of this theorem 6.2. Okay, so to prove that f is Riemann integrable on 0 to 2. We apply theorem 6.2. Let's apply theorem 6.2. Okay, so how does it work? What do you suppose my first sentence is going to be? Let epsilon greater than 0 be given. Absolutely, it's my rubber stamp. It's kind of my rubber stamp that I'm working with here. Okay, so we kind of can start off with that, and our job now is to find a partition. And this is normally where we would go off onto some scratch work and try to calculate what partition should it be. I'm gonna hope that I can use one of these partitions, where I chop up my interval from 0 to 2 into n equal pieces, each of width 2 over n. That's gonna be the idea. Okay, so maybe let's do some scratch. Let's go back to the kind of the old-fashioned approach to this. Before I continue with this proof here, I would like to find an n such that the partition piece of n will have this property right here. Okay, so so let's let n be a natural number, and let's consider p sub n. Let's consider this partition. And in this partition, the delta xi's, which are the widths of the subintervals, I still have it here, right? They're each of width b minus a over n. So these are going to be b minus a over n, which in this case is 2 over n. So the delta xi is just 2 over n in this context. Okay, so what I'm going to suggest that we do is we chop up this interval into n equal pieces. Now, the important point is that the place where there's a big change in the function is right when x equals 1. There is a subinterval here that has 1 in it. Somewhere 1 will be part of one of these subintervals, right? So what we could do is we could say, let's find k such that xk minus 1 is less than or equal to 1 is less than or equal to xk. These are not going to both be equal signs, because obviously xk is not the same as xk minus 1, but it's possible that the 1 could actually be on the endpoint of the interval here. Question? We're gonna try to find a specific value of n. Yeah, that's gonna be the goal, because we have to come up with a partition, which means we need to come up with an n value. Yeah, we're looking for an n value right here. Okay, now guys, as long as I does not equal k, as long as I'm not looking at that particular subinterval that has the 1 in it, if I'm to the left or if I'm to the right, would you agree that if I is less than k, you're over here and your function is constant? And if I is greater than k, then you're over here and the function is constant. Which means that on those subintervals, the capital M's and the little m's are just equal to whatever the y value is. Right? So if for I not equal to k, m sub I is actually equal to, the capital M sub I is equal to little m sub I. Right? I mean, here's an example. Here's a value of I. On this little subinterval, the capital M and the little m are both equal to whatever that number is, which is 1, I think. So the big M and the little m are the same. You with me? The only place where the big M and the little m are going to differ is on whatever subinterval has the 1 in it. Right? That's where you're going to have trouble. Let's see. I need more room. Maybe I'm going to have to come back over here. Okay. I'm still on the scratch. So we still are looking at the scratch here. Just like before, we're still on the scratch. Let me get my camera. This up here so people can see. Okay, so for I not equal to K, that is the case. However, for K itself, for the K value itself, this is where the big M and the little m are different. Whichever subinterval has the 1 inside of it, which would be this subinterval. What is the big M for that subinterval? This y value is 3, that's the maximum value, the supremum value. And what is the little mi, for the little m sub k, I mean, for that particular subinterval that passes through 1? This number, right? -1. So that's where there's a difference. That's where there's a difference. This is 3 and this is -1. That's the key point. See the difference? All of the other subintervals, the big M's and little m's are the same. And what's important about that, guys, is that theorem 6.2 is gonna have you doing this calculation. We're gonna take the UPN of F minus LPN of F. We want it to be less than epsilon. That's what theorem 6.2 requires. But what is it actually? This is a summation, I going from 1 to n of, I'm gonna do the subtraction inside the summation. Big Mi minus little mi times delta xi. That's actually what this difference is. So far, so good? Now, all of the delta xi's are the same number, which is 2 over n. They are all of these guys are just 2 over n. I can take that outside of my summation. 2 over n times the summation, I going from 1 to n of big Mi minus little mi. However, most of these terms are 0. As long as I does not equal k, big Mi and little mi are the same. So when you subtract them, you get nothing. There's only one term out of this summation. There's only one term where the big M and the little m give us different values. And we already looked at that. It's the kth subinterval. And in that case, we get a 3 and a -1. When we subtract those, we get 4. So actually what this is 2 over n times, really it's 0 plus 0 plus ... And then there's a 4 somewhere in the middle, and then 0, 0, 0, forever 0. Most of those differences are 0, except for one particular time. And so this comes out to be 8 over n. You with me? So we want that to be less than epsilon. Ultimately, theorem 6.2 says for all epsilon, we have to find a partition. In this case, I'm going to find my partition on the basis of this n. And if we work this equation around, n should be what? Greater than 8 over epsilon? Something like that? N would need to be greater than 8 over epsilon right there. And so now I'm ready to come back to my proof. That's the end of my scratch work. With me? Let epsilon greater than 0 be given by the Archimedean principle. Goes way back to February. By the Archimedean principle, find a natural number little n such that n is greater than 8 over epsilon. So now we're back to the main proof. We're going to find an n that's greater than 8 over epsilon, and then consider the partition E sub n, which is in the set of partitions of the interval from 0 to 2. And now we basically refer to the scratch work. So that then U of P N F minus L of P N F is less than epsilon by the scratch work. By the scratch work. So as long as you chop up your interval from 0 to 2 finely enough, as long as you make these subintervals narrow enough, then the one term in this sum where the big M's and little m's don't agree, they don't agree here. But if you make that subinterval so small that the difference here, which is 4, gets multiplied by 2 over n and becomes as small as you want it to be, then the entire UPN minus LPN, UPN of F minus LPN of F will be less than epsilon. Question?
So for our x of k, if one was equal to x of k, would we just like shift it over one? Cause then wouldn't our minimum be 1 and not -1?
So you're bringing up a very good point, which is what she's pointing out is that if 1 itself happens to be where we chop, like if there's a chop right on that point, so here's 1 right here, and we happen to have our subintervals like that, then I was gonna see if I could slip this by on you guys, but you caught me. Then there's actually 2 subintervals that are problematic, not just 1. Cause you've got this point, this 1 is kind of on the edge of both of them. And so in that case, what would happen is your big M's and little m's would maybe disagree in 2 subintervals, not just the kth one, which is what I'm saying over here. That could be a little bit of a problem. It would mean that we would maybe have 2 terms where we would have numbers here other than 0. Okay? And so we would have to modify this slightly. So you're right. Is there a way we could get around that?
Not be less than or equal to? Or like if it was just less than, then you'd have to like.
Yeah, could we just choose an n such that when we chop up our interval from 0 to 2, we don't actually hit 1? Let's just do that. What kind of n's would that work for? So what am I asking? What I'm asking is if I take the interval from 0 to 2 and I want to chop it into n equal pieces, but I don't want it to chop right at 1.
Be any odd.
Any odd value of n would be safe, right? So as long as n is odd, you won't be chopping right at 1. If I'm chopping this into 4 equal pieces, I'm gonna hit 1. If I'm chopping this into 10 equal pieces, I'm gonna hit 1. But if I chop it into 7 pieces or 15 pieces, or anything like that, I won't actually hit 1. So you know what we're gonna do? Because I don't want my proof to be wrong. Find an n in the natural numbers such that n is odd and n is greater than 8 over epsilon. You guys all getting this down? I'm probably gonna grade this one, so everybody who's here today is gonna get, full credit on this, I'm sure. As long as you're paying attention, but yeah, n being odd is actually a good thing to include there. As long as n is odd, are we good though? Then everything with the scratch work is great. This calculation works great and we don't have a problem. And Cozy?
You spend one more time after that specific k, the big M k equals 3 and little k is -1.
So whichever subinterval this is, here's 1 right here. There's a subinterval here, and now we're gonna assume that it doesn't chop right at 1. In this subinterval, this is the kth subinterval. The big M is the supremum of all of the outputs within that subinterval, and it's right there, which is 3. And the minimum value is gonna be down here somewhere, which is -1. That's it. Yeah, and everywhere else on any other subinterval, the big M's and little m's are all the same. So the UPFs and LPFs add up the same amount for both of them. So am I done with this problem?
No, because we still have to find the interval.
I still have to find the integral. Yeah, I still have to find the integral. Oh my gosh. Do I have enough time for that?
Yeah, we have 7 minutes. Good.
We have plenty of time. Timer's running. No, we can definitely do it. The downside of this theorem is it doesn't tell you the value of the integral. It just tells you that the function is Riemann integrable. So I've done this part. I'm gonna check there, but I still have to actually evaluate the integral. So here's what I'm gonna do to actually evaluate the integral. So to evaluate. Actually, you know what? I'm gonna do it over here. I need more room. So I'm gonna evaluate the integral, but I need a little bit more room. So let's just give ourselves plenty of room here. Yeah, let's just give ourselves plenty of room. Okay, so, can we actually calculate, so to evaluate the integral from 0 to 2 of f, let's consider what is the value of the upper sum for the partition piece of n, where again, I'm assuming that n is odd. So consider for odd n, let's consider this upper sum. The upper sum is, of course, the summation, I going from 1 to n of capital M sub I times delta xi. And the width of each subinterval is 2 over n. I'm going to factor that out. And so I'm just calculating the summation of all of the big mi's. So I factor out the delta xi because they're all equal to 2 over n. And so this is 2 over n times what? Well, the big mi's for the first few subintervals over here on the left are going to be equal to 1, right? And then eventually there'll be one term where the big mi is equal to 3. And then there'll be the rest of these terms here where the big mi is equal to -1. So it's a bunch of 1s followed by a 3 followed by a -1. You see? So we have 1 plus 1 plus 1 a bunch of times. Then we have a 3. And then we have a -1 and a -1 and a -1 a bunch of times. Let's try to figure out how many times it is. Remember, this was the kth subinterval. That was for I equals k. So this is for k minus 1 of the terms. We would have a bunch of 1s. And so then this is the kth term. And then what are the remaining terms? How many terms are left? There's n terms total. I've got k minus 1 of them here. I've got one more over here. I think this should be n minus k. I think it should be n minus k. So let's just add this up then. So this is 2 over n times, I have k minus 1 ones added together. I'll add up to k minus 1. And then I have a plus 3. And then I have how many minus 1s? I have n minus k of those. So that'll be actually subtracting n minus k. All right. And does that simplify? I hope so. So 2 over n times 2, right? Minus 1 plus 3 is 2. And then I have 2k minus n. I think that's what I have. Let's clean that up a little bit more. So this is 2 over n times 4k minus 2n. And I'm going to go one more step, guys, if you don't mind. This is 8k over n minus 4.
Why are we multiplying 2?
Sorry, why is there 2 here?
Because 3 plus -1.
Oh,
No, I don't.
that's
This should all
2,
be-
yeah, I think I've screwed up, sorry, let's go back, sorry. See, I'm under pressure. You guys are making me nervous. 3 minus 1 is 2, I should be adding, thank you, adding 2k minus n, oh my gosh, I thought that was looking weird.
Call yours.
That should have been plus 2k minus n, thank you. And now, that's 4 over n plus 4k over n, and then minus 2. Okay? Right? Okay, what about the LPN of f? This is the summation, I going from 1 to n of little mi delta xi. Again, I'm gonna pull out a 2 over n. And I'm gonna jump straight into the calculation here. Again, I have a bunch of 1s. And then the kth term has a little mi value of -1 here, right? Of -1. Okay, and then that's the kth term, so there's k minus 1 here, then we have the kth term, and then there's a bunch more -1s. Okay, so I'm gonna go a little quick here, this is 2 over n. And I'm gonna add all that up, I have k minus 1 on the positive side. And then I have to subtract at the quantity n minus k plus 1, I believe. Yeah, and so let me simplify that as well. So this is 2 over n times -1, and there's another -1, so it'd be -2, right? Plus 2k minus n. Think I got that right. And so that becomes -4 over n plus 4k over n minus 2. Okay. So what is the answer supposed to be? It should be 0, shouldn't it? So if I actually think about doing this integral, this is a rectangle of width 1 and height of 1, and this is a rectangle of width of 1 and height of -1. Shouldn't those cancel out? This point doesn't actually matter. So I might have flubbed this up a little bit. Because it looks like as n goes to infinity, which is what I was gonna do, if I let n go to infinity, then you see that these LPN of f's are approaching -2, and the UPN of f's are approaching -2, so I don't like this very well. 2 over n is 2 plus 2k minus n.
I think it may be the option.
Why don't we do the following? I'm not gonna ask you to turn this part in. I'm going to sort this out and just fix it up next time. It's something, I mean, I'm looking at my solutions here. I tried to do it a slightly cleverer way, which obviously didn't work out too well. I don't see what's wrong with this, to be honest with you. I don't see what's wrong with this. The difference between these two, if you were to subtract them from each other, you would get the 8 over n, which is what we had gotten earlier from the scratch work. So the difference is right. But it appears that the integral is coming out to -2, which is not the right answer, of course. So what is wrong with this? K is just some. Oh, that's the answer. The K value is the one right in the middle of the entire partition, isn't it? So if there's n subintervals, then K should be n over 2. It should be halfway along. So K is not just some random spot in the interval, it's because 1 is exactly halfway. So here, K is equal to n over 2. If I plug that in, since 1 is in the middle. I'll just finish this up really quick, guys. So K is just n over 2. So U of PNF becomes 4 over n. If I put n over 2 there for K, doesn't it just cancel out with the -2? This is all you get. And L of Pn of F is negative of 4 over n, and everything else totally cancels out. Yeah, that's how this works. So you have negative 4 over n, less than or equal to. Okay, so that's the LPN of F. That'll be less than or equal to the supremum of all of those LPFs. So this would be, the supremum would be the lower Riemann integral, which is always less than or equal to the upper Riemann integral. And the upper Riemann integral is less than or equal to any of the UPFs. Right? So the upper Riemann integral is the infimum of the UPFs. So here's a UPF, and the infimum would be a lower bound of those. So there you go. Now, guys, just hit this with the squeeze theorem. So as n goes to infinity, negative 4 over n goes to 0, 4 over n goes to 0. So everything in between has to get also squeezed to 0 as well. And so finally, last step, and then I promise I'm done. So by using the squeeze theorem, think of this, here's a sequence, they both converge to 0, and each of these is a constant sequence. And so it's also converging to 0, and the constant sequence has to converge to whatever its value is. So this is equal to 0 is equal to the upper Riemann integral. That's the rest of the solution. I was missing the point that K has to be n over 2. Right, it's exactly halfway along that whole interval. So let me get that on the camera as well. Sorry to give you an extra 5 minutes, but I just stumbled through that much worse than I expected to. Does it make sense though? Reasonable enough? Okay, I'm gonna go collapse for a little while. I will see you guys. If you have questions about the chapter 5 problems, feel free to stop by my office hours today. Be glad to help you out. On Thursday, we'll prove this theorem and take it a step further from there. I will see you then. If you start the homework early, you can ask questions on Thursday about the next homework.